Okay, so I guess we can get started now. Oh, whoops. I guess we can get started now. So today we're going to be continuing with invariants. If you didn't see the recording for last class, it's uploaded to YouTube, so you can like check it out on our class page. Um, anyways, why don't we get started with some problems? If you don't remember, invariants are basically something that do not change, and monovariants are something that change in a very specific way. And we can use these to solve proof problems by like showing certain things are invariants, and then like that can be a useful step in solving the problem. So why don't we get started with another coloring problem? So if you remember from last week, we covered some colorings, like some common colorings are um, like the checkerboard coloring. Like these are just like some standard examples that show up a lot. So like there's the checkerboard, right? And the checkerboard coloring is just coloring things black and white. So for example, if you have like something like this, you color it like black and white, like a chessboard, and this is really useful in some examples. And then you can also have something like um, N color, the N coloring. Let me go to a different slide for this. So you can have like something like the N coloring. So basically, what this is if you have like a very big grid, and I'm just gonna say the colorings are 1 through N. Um, I don't actually have N colors. But anyways, if you draw this board, hold on. What it does is you start with like a 1 in the corner at the top, and then for each diagonal, you like add 1. So like you would go here, and then so for however many colors you have, you go to that color. So you would have like N's over here, and then the next diagonal would be 1's, right? So, in an example we did last week was the 3 coloring, which is if you only have 3 colors instead of N. And this is always, and that was like useful for showing that each 3 by 1 or each L shape, I think it was either 3 by 1s or L shapes, have exactly one thing of each color. So let's go. Um, I'll introduce a different type of coloring in this next problem. So this next problem is if you have a 9 by 11 board, um, then and you can tile it with 2 by 2 squares, um, or like these L-shaped trinomials. Then what is the smallest number of ah, okay. um, want least number. So we want the least number of shapes to fully cover the board. Um, so whenever you see one of these types of problems, like this, the simplest way would just be to like try to cover some boards. And if you want the least number of shapes, you want more of these, right? You want more of these because these cover more area because it's like one shape, but it covers 4 squares instead of just 3 squares. The coloring that we want to use is coloring 2 by, I call it coloring mod 2 by 2. This, uh, So instead of like the N coloring that we had before, which is where you have like every diagonal is a different color. In this coloring, you look at each 2 by 2 square. So for example, why don't I just start with a big grid? Um, for some reason. What you do is you like color. I'm just gonna use the colors 1 through 4 because there will be 4 colors. So you do something like this. So So for each 2 by 2, you have the colors 1, 2, 3, 4 in like this pattern. So it's notice that even though this is 4 colors, it's different than the 4 coloring, because the 4 coloring would be something like 1, 2, 2, 3, 3, 3, right? So in this is like slightly different, but it's like different in an important way, and we'll see in a moment. The reason why this coloring is so nice is because if you have like a square or something, if you have a square, so like if you notice each square, each 2 by 2 square, um, has one of each color, right? No matter where you put it on the board. So if you were only caring about 2 by 2 squares, then you can use this as an invariant. Now, what about L-shaped trinomials? Why don't we see if you put something like this, and it doesn't have to look like, you can also rotate the trinomial, so you can have it something like this, right? But um, but no matter how you rotate it or you put it on the board, you have one of 3 colors. So you have 3 different colors, and you have like one of each of those colors. And so that means if you take a specific color, like let's say we only look at the squares of color 1, then each shape can only cover one square of color 1 for the color 1, right? So this already gives us a lower bound, so why don't we just like count it? So like if you look at the 9 by 9 rectangle, I'm not going to draw the whole rectangle, but if you just like kind of visualize it, it's well, first of all, it's odd by odd. 9 and 11 are both odd. So why don't we just count the number of things of each color? So I'm just going to draw a smaller board, not a 9 by 11, because like you can just like see a pattern from just like a smaller board. So it should be odd by odd as well. So why don't we do a 5 by, let's do a 5 by 7. So why don't we like do some coloring? So obviously the number of squares of each color is not always the same, right? So is not the same for each color, I should say. So like, why don't we do this? So if you notice, like the number of blues and reds are not the same. It's also different from like the number of greens. And so did I miss it? Yeah, I missed the blue. And finally we have the yellows. I think you can, right. So you notice that the yellows, there's not very many yellows, right? There are only 6 yellows. Because there are 3 columns with yellows and 2 rows with yellows. So there are 2 times 3 equals 6 yellows. So if you look at the 9, so like the number of yellows would be 2 times 3 equals 6. In the 9 by 11 board, the number of yellows would be, I think it would be 4 by 4 times 5, which is, yeah, it would be a 4 by 5, which is 20. You would have exactly, wait, is it 20 or, yes, I think it's 20, right? Wait, no, it should be 30. Wait, was it 20 or 30? I don't remember. Right. Okay, no, I'm sorry. You want to look at the colors with the most number of squares. Yeah, you want to look at them. So like let's look at the reds. So how many there are exactly 12 reds, because it's like a 3 by 4, right? So there are exactly 12 reds. And so in a 9 by 11, number of reds would be 5 times 6, which is 30, right? So just from here, we would need exactly at least 30 shapes, because for each red square, like a single shape, like either a 2 by 2 or an L shape, can cover at most one red square. So that means that if you have that means that for each red square you need at least one shape, right? So if you have 30 red squares and each shape can cover at most one red square, then you need at least 30 shapes. And we can actually do this using 9 2x2 squares and 21 L shapes. I won't do it right here because you can just like try to fit it up. But like this is but like if you were actually doing this problem, you should definitely check that this works. Why don't we do Okay, so why don't we do this is a simple example, I guess. But like if you have a m by n chocolate bar, so like I guess it's just like an n by n grid, like because chocolate bars are like in the shape of a grid, but and what you want to do is every move, if you have like some bar, you can break it along the grid line. So this would become like two things, right? So the question is, the game ends when, so like there's two players, A and B. Each turn equals one break, and that means, and each time you do the game ends when the game ends when you can't break anymore. So like when everything is so game ends when only one by one's left, right? So why don't we just like try it on like a small board, like a 3x4. So I'm just gonna choose a line to break it on. Let's say we choose here. So then this would be a 3x1 and a 3x3. And we can just like break this. We can break this into like a 1x1 and a 2x2. So this is like kind of a dumb example because every time you make a move, the number of different pieces goes up by 1, right? And at the end, you have exactly mn pieces. So in total, there are mn minus 1 moves. So total, right? Because you start with one bar, and then every time you break, you go from one piece to two different pieces. So you have m times n minus 1 moves. And so that means, right, and the person who moves last wins. So that means the first player wins only if, I should say, the second player wins only if m and n are both odd, because you want mn to be odd. Why don't we try this example? So you have okay, so okay, so you have like this pentagon, and at each vertex of the pentagon you have a number. So I'm just gonna say this: A1, A2, A3, A4, A5. Integers, I should say. They're integers, so I'll just say integers. And then you have that the sum of AI is 2011. And you can make moves. So a move would be I think you add 2m from you add 2m to a vertex for some m, and then you subtract m to two opposite vertices. So like, what I mean by two opposite vertices is like the two vertices that are like the farthest away from that vertex. So like if you have something like this, you would have plus 2m, and then you would have something like minus m on the other things. And you can like choose where the m is and what the value of m is. So basically what you want to prove is that, okay, so first of all, you win. Well, first of all, a simple invariant, before I finish saying what the problem says, is that like the sum of AI is always the same, right? Because you're adding 2m to a vertex and you're subtracting m from the other two vertices, so the sum is always the same. So you win. You win when like something like AI equals 2011. Other vertices equals 0. So you want to make 4 of the vertices 0 and the fifth one 2011. And so the question is, where can you win on this? So where can you where is this last vertex? Where can the last vertex be? Like where can the AI equals, or sorry, I should say where can the 2011 be? So like if we are to make 4 of the numbers 0 and one of the numbers 2011, where can the last number be? So we want to find some type of invariant on like this, I guess this pentagon, like something that's different from just the sum of all the numbers, because that's like, that doesn't really help us. So I guess like one of the strategies we went over last week was just to break it down to the most simple case possible. So the most simple case possible in this case would be plus 2m and minus m as some of the opposite vertices, right? And so basically the idea is, you can kind of think of it as rotation, right? So if you subtract m from like two vertices, then what you're doing is you're kind of like rotating, you're kind of like moving m things like clockwise. So like you're moving m things clockwise, and you're also like moving m things counterclockwise, right? So it kind of balances out if you think of like this rotation idea, right? So we want to somehow like quantify this rotation idea, and so like how do we like kind of visualize this? So basically, we want to make some invariant, right? So we want an invariant, and invariants are usually like a value, some invariant. Invariant that is like some value. Right? And the value does not have to be a number. It can be like anything, as long as it doesn't change, right? It could even be like something, or I won't say that. But anyways, so basically, if you want to capture this rotation idea, so why don't we like break this down even farther? So if we're rotating something clockwise, you're adding 1. So like clockwise, you're adding 1, and then counterclockwise, you're like subtracting 1, right? So if you, or I guess m, because you're moving m. And so like if you have something like here, or like let's draw a pentagon again. If we have something like, if we move 1, let me use a different color. If we move 1, actually I'm going to erase this because because you don't really need the m. So clockwise would be plus and counterclockwise would be minus. If we move 1, then the value of our invariant plus adds 1, right? So that means that the invariant increases. And if it goes counterclockwise 1, so like if you do the reverse, so you go opposite 1, then invariant decreases. And that's basically the idea. So how can we kind of characterize this invariant? Because now we have like these like very basic properties of an invariant. So once we have these very basic properties of an invariant, there's only like one possibility for what the invariant can be, right? So I guess the way you do this is, well, first of all, if you move something clockwise, if you move like one, like I guess if you rotate, I guess if you're moving like one thing, I guess you can visualize it as stones instead of like numbers on the vertices. Like you can have some number of stones at each vertex. If you take a stone and then you move it clockwise one vertex, then the invariant increases by 1. But if you do this 5 times, then the invariant goes back to itself, right? So what you really want is something mod 5. So you want something mod 5. Mod 5. And so now your invariant should be something like this. Like the only possibility would be something like A1 if you have something like A1, A2, A3, A4, and A5 as your pentagon, right? Then you want A1 plus 2A2 plus 3A3 plus 4A4 plus 5A5 mod 5. Let me erase the A1s through A5s because we're getting in the way. So you want this mod 5. So you want this entire value mod 5. And this is what your invariant is, right? So why don't we like kind of show that this actually works? So if you have like, if you add 2m to A5, or sorry, A2, so A2 plus 2m to A2 minus m to A4 and then minus m to A5, then the coefficient of A2 is 2, right? So the invariant, this becomes plus 4m. The coefficient of A4 is 4, so this becomes minus 4m, right? And then the coefficient of A5 is 5, so it's basically 0 in terms of mod 5, so this would be just 0. So then in total, the invariant would change by 0. So no matter how you make moves, the invariant stays the same mod 5. So now we want something to be, if we have the invariant mod 5, like let's say, well, first of all, let's just say the invariant is I. So like let's say I is congruent to whatever this is mod 5. And let's say, I don't know, like let's say, just to see like how this solves our problem, let's say like I equals 3. The number 3 doesn't really matter because it's like symmetric, right? All the vertices are symmetric to each other. So let's say I equals 3 without loss of generality. And you want 4 of the numbers to be 0, and you want one of the numbers to be 2011. Then A3, you have to have A3 equals 2011, right? Because you want this sum here to be, you want this sum mod 5 in the last slide to be 3. So and if 4 of the numbers are 0 and one of the numbers is 2011, then A3 has to be the number that's 2011. So from this invariant, we know exactly which vertex we can have as this 2011, and there's exactly one vertex that we can have this 2011 at. Okay. Okay. Let's move on to another example. Okay, so in problem three for today, I think this is the third problem, or maybe it's the fourth problem. I think it's the fourth problem. Anyways, so if you remember from last week, we had this problem where if you had a graph where each thing has, or like I guess in the flavor text, a party where each person has at most 3 friends, and friends go both ways, we can split them into 2 groups such that every person has at most 1 friend in each group. So now we have a group of people that each have more friends than enemies. So everyone has more friends uh, than enemies. So everyone has more friends than enemies, and we want to prove that. We want to prove that we can seat them around a table. Table. So like you would arrange them in like a circular table, and you would have like something like this. I guess not a good drawing, but like, and then no neighbors are friends. So like no 2 people sitting next to each other are friends. And just like how we did that problem, we want some monovariant this time. So we basically, the sketch would be start with random seeding. If something violates our condition, if exists 2 neighboring enemies, or sorry, neighboring friends, can have monovariants. So first of all, what is the monovariant? So I guess a good monovariant would just, we have to decide what our monovariant is. So a good monovariant would just be the number of neighboring enemies, right? Or sorry, would be just the number of neighboring. So the number of neighboring friends. So how do we do this? First, let's just kind of visualize what the circle looks like. So if you have like this circle here, and you have like 2 friends, let's say this is X and this is, or I'll just say A and B, and these guys are friends, then we want to somehow separate A and B so that it doesn't violate our conditions. So how do we do this? Well, basically the idea is you take you want to find some like X and Y I'll just say x and y, where x and, or I guess you want to find some x and y. Let me write this. You want to find x and y where b and x are not friends, or not a and x are not friends. And then b and y are not friends. And then what you can do is you can take this thing here and then reverse it, right? So reverse. Like, I guess flip it. So like if you had something like, if the things between were 1, 2, 3, all the way to n, then if you flipped it, it would be something like x, n, all the way to 2, 1, and then b, right? So you would basically just reverse that. You would just take this chunk and you would reverse it, and, or I guess flip it. And then when you flip it, the only neighbors that change would be a and b are b and y become neighbors, and then a and x become neighbors, right? So if we have that a and x are not friends and b and y are not friends, then we're good, right? Because we basically just eliminated one pair of adjacent friends. And so so like how do we show that we can, like, such an x and y always exist? Well, we have to use the condition that they gave to us, which is that everyone has more friends than enemies. So first of all, if everyone has more friends than enemies, well, a and b are enemies, so that's already like something. So that means that out of the remaining things, let's call them x1, or yeah, let's just call them x1, x2 in order, all the way to x3, all the way to xn. So we basically want to find some like xi here, and then some xi plus 1, right? And we want to find like an xi and an xi plus 1, where like we can show that b and, so first of all, I think it's b and x plus I don't want to be friends. So like I'll just like draw these lines. And so first of all, out of x1 through xn, a has more friends than enemies, and the same thing is true for b. So from x1 through xn, b has more friends than enemies. And so let's mark all the non-friends of a. So there are at least n minus 2, or I guess greater than n minus 2, n over 2 non-friends. I'll just use non-f of a. And so that means that, why don't we look at the number of, so if we mark all the friends or the non-friends of a, we can also mark all people who are one person clockwise to all the friends of a, right? Because if like xi is a non-friend of a, then for example, then xi plus 1 would be one person clockwise from xi, right? So we want to mark all of our xi plus 1s, and there are greater than n over 2 possibilities for xi plus 1, right? And there are also greater than n over 2 non-friends of b. So if those, that means that since the sizes of those two sets together is more than n, then they must overlap, right? Because if you have two sets, subsets of x1 through xn, and they both have sizes greater than n over 2, then they cannot be disjoint, right? Because they're all subsets of a set of size n. And so that means that xi and xi plus 1 always exist. And you can always do like this flipping trick. Why don't we do another easy-ish example before we move on to like some harder problems? Uh, so um, so we basically, what we do is we start out with um, four numbers, x, y, u, and v, and the values that they take start out as a, b, a, b. So this would be initial. So this would be step 0. And for each step, you apply the Euclidean algorithm to a and b, or x and y. So if basically what happens is if x is greater than y, then what you do is x goes to x minus y, right? Y goes to y, but the thing is u goes to u plus v, and v stays v. So basically what you're doing is you're applying the Euclidean algorithm to x and y, and you're doing the opposite thing to u and v. So it's like some kind of process. So here x goes to x, and then y goes to, first of all, everyone knows what the Euclidean algorithm is, right? Euclidean algorithm is just a way to find the GCD, like the greatest common divisor of two numbers. So if you have two numbers x and y, why don't I just use the numbers 15 and 10? 15 is greater than 10, so what you do is you take the numbers 15 and 10, and then you subtract the smaller number from the bigger number. So you would go from 15 and 10 to 10 and 5. And then from there you would subtract 10 from 5, so you would go to 5 and 5. And then if the x equals y, so if the two numbers are the same, then you stop. Basically, that's what. And so in the second step, if x is less than y, so then u stays the same, and then v goes to u plus v. So every time x and y change, then you do like basically the opposite to u and v. Let me add another board. So first of all, we know that when x at the end, so we care about the end state. I haven't like said what the problem is asking for. So the end state is x equals y, right? Because we stop at x equals y. And from the Euclidean algorithm, we know that at the end, x and y equals GCD of a and b. A and b is what this x and y started out to be. So we want to prove that u plus v equals 2 times LCM of a and b. That's what we want to prove. Okay, so and if you just think about it, it kind of makes sense, right? Because if you're applying the Euclidean algorithm to x and y, you're getting the GCD. But then if you're doing the opposite, then you should get something like the LCM, right? So what is a good kind of I guess monovariant? Well, invariant. In this problem, we would want to use an invariant, right? Because we want to somehow prove that something stays the same, and then if we know x and y, then we can somehow use the invariant to infer something about u and v, right? So why don't we just like try some simple things and then see what happens. So let's start with x. So the most simplest, as we talked about last week, the most simplest strategy would, the strategy would be start with the most simplest thing possible. So let's say x is greater than y at some time, then you would then the next step would be x goes to x minus y. Y stays at y, and then u goes to u plus v, right? And then v goes to v. So what is an invariant here? If this just happens in general, if you're just using this, can you show that something is invariant? And the answer is, I think you can actually. Let me think about this for a second. Yes, you can. So basically the invariant would be like you can, if you were, you can kind of just notice this, xv plus, well, first of all, I'll just like write the invariant xv plus u times y, x times v plus u times y. This is invariant. And if you're looking for an invariant, first of all, x and y should be symmetric, and u and v should be symmetric, right? But x kind of relates to u, because if you're changing x, you're changing u, and then y relates to v. So you kind of want to keep that symmetry in mind. And so like one like thing you might guess is just the value x times v plus u times y, right? And you can check that this is invariant because now if you have something like, if you do the transformation, then you have x minus y times sorry, it should be x, yeah, right, xv. So x minus y times v, because v doesn't change, times y times u plus v. So this would be xv plus yu minus yv plus yv. So this. So then this just cancels and it's still the same, right? So from here, we've just looked at the simplest process in our kind of like our system. So how can we like use this to kind of show that our conclusion that in the end we want to show that u plus v is 2 times the LCM of a and b. So let's go back to our end state. If you remember from the Euclidean algorithm, you get that x equals y equals GCD of a and b. And then u, so we want to somehow get u plus v. So first of all, xv plus yu is invariant, and this equals, if you remember from the start, this equals 2ab, right? Because at the beginning, this invariant equals 2ab, so now it should still equals 2ab. So that means that x equals y now, so we can factor this. So GCD of a and b times u plus v, we're just factoring here, equals 2ab, right? So that means that u plus v equals 2ab over GCD of a and b. And if you remember, ab over the GCD of a and b equals the LCM, so this equals 2 times LCM of a and b. So this is how we get our answer. Okay, so why don't we go over like a couple harder examples? I guess that one was also kind of hard, but why don't we go over some harder ones? I guess this one's not too bad, but it's kind of tricky if you're not thinking about it the correct way. So you have a unit square, you have a 1 by 1 unit square, and ants travel at one unit per second. So it doesn't say like how big the square is, but like you only care about the units. So I guess this would just be 1 u for 1 unit, and then ant crawls 1 unit per second. All ants. There are multiple ants, so there are like a bunch of ants that crawl at 1 unit per second. And when ants meet head on, so like if they were going like opposite directions, then they both turn 90 degrees. They both turn 90 degrees, I guess, to the right, and then they keep on moving. So if ants hit turn 90 degrees, so they must hit head on. So like hit head on. So like they're moving in opposite directions when I say head on. Then turn 90 degrees and keep on moving. And so so you start out with some finite number of ants. Well, actually, you can even have infinite number of ants. I think it doesn't really matter if it's finite or not. So the question is, now that I've like set up the problem, so if you notice, like there's usually in these problems, there's usually like a large setup, like a long setup before they actually ask the question. So you wanna so the question is, find smallest. So we want to find smallest t, such that after t seconds, all ants off the board. So like what I mean by that is if the ant like if it hits the edge of the board, then it just like walks off the board, right? And it just keeps on going because the ants don't turn unless it hits another ant. So why don't we just like try some things? If you only have one ant, then it just like moves off the board, right? So I guess another way to think about this would be, since an ant travels at 1 unit per second, then the time it travels is the same as the distance it travels, right? So we can just care about the distance. So if there's only one ant, then the maximum it can travel is just one unit, right? Because it just goes straight 1 unit and then it drops off. What if you have like some head-on collisions? Well, why don't we draw our grid again? You can have something like this, right? If it hits like this, then one ant goes off, and then one ant. I should use different colors for the different ants. So like this ant turns 90 degrees, and then this ant goes this way, and it turns 90 degrees, right? So here, the blue ant would have traveled 3/2 seconds, right? Can you have something like, but now we're seeing that ants are turning, right? So it can be more than, it doesn't just walk off the edge. It can turn and stuff. So could we have some bigger number? Like could we have something like 2? Like could the ant go like here and then here? But the thing is it can't, because then if you look at another ant, you would have had something like this, right? And if you have something like this, then it's not possible, because how did this ant get here after 1 second? So, like, yeah, I'll just say, how did this ant get here? And that's an important question. Yeah, okay. Okay, so another thing we can notice is that if you have 2 ants like this, right? If you have 2 ants, I guess I can use 2 different colors. Let me use red and blue again. If you have 2 ants like this, then they turn 90 degrees, right? So it goes something like this, right? So they turn 90 degrees. After they turn 90 degrees, the red ant is facing downwards and the blue ant is facing upwards, right? Because they just turned 90 degrees. But notice that this is the same as each ant turning 90 degrees to the left, right? If the red ant is now traveling upwards and the blue ant is traveling downwards, then it's the same. Oh yeah, I should say that, I forgot to say this, that all ants traveling northwest in like the northeast southwest kind of thing. So like you can't have an ant going diagonally. It has to be like northeast, south, and west. Well, actually, now that I think about it, does the problem still work for if the ant is not, actually, I don't know. But anyways, all the ants have to be traveling like in some cardinal direction, so it's either left or right or up or down. So anyways, I guess the point that I'm trying to get at in this slide is that It doesn't really matter which ant goes in which direction. It just matters that if you have two ants that hit each other, that are going left and right, then one of the ants goes upwards and one of the ants changes directions to go downwards. And it doesn't really matter which ant goes which. So I guess one thing the takeaway from here is that you shouldn't think about each ant as its own person. You should kind of like the ants kind of blend together, right? Like they don't actually, the identities of the ants don't actually matter in a certain sense. Um, so uh, so now let's kind of let's try to like solve the problem. So anyways, if you experiment some more, the answer is actually 3/2. So what if we had some, so I guess we can go for, it's not clear what the invariant is now, so we should just go over like kind of, or I guess at this point you would not know to use invariants because it's not really clear that you would use invariants. So at this point you should just like think about how do we like prove this, most likely using a proof by contradiction, right? If you have like some ant that goes over 3.5 seconds, then like something bad must have happened before, right? Something illegal must have happened. So let's look at some time. So let's look at some time t is greater than 3/2. And let's say we have an ant right at the edge of the board at time greater than t equals 3/2. So like let's say this is our ant, our little arrow here, that's our ant. And the time is greater than 3/2. So why is this bad? Well, we'll see. Why don't we turn back the time? So why don't we do the time in reverse? I guess that's the idea of the problem. You want to do like some reverse time thing, right? So if you reverse the time, what happens? Well, the ant travels backwards. So I think I should use a different color for the ant. So we have our ant and it's traveling backwards, right? So it's traveling backwards. And then before it reaches the other edge, it must meet another ant, right? Because then you have to like, if you're going here, then you have to like turn, right? So let's say the ant turns like this. If the ant turns like this, then you must have another ant, right? That means that suddenly you must have a red ant, right? Because how else would the ant have turned? So if this ant turns, then you have to have an ant that turns in both directions, right? So now instead of just following the blue ant, we should follow both the red and the blue ant. Right, so it doesn't really matter which ant is red or blue. Like we said before, if the red ant is on top, right here the blue ant is on top and the red ant is below. But if we change it so that the red ant is on top or the blue ant is on the bottom, it doesn't really matter, right? So I guess you can just like think about it as you can just follow one of the ants. So I guess we don't really need the red ant. We can choose which, because only one of the ants matters, I guess. And so let's just follow the blue ant. So if the blue ant splits here, then we can choose which way the blue ant turns because it doesn't matter which ant was the blue ant. So let's say the ant turned right here. So let's say this is the blue ant and there's another ant here. I could just have easily had the blue ant being on the right and the red ant being on the left, but then the blue ant would have much longer to go, right? So if you look at the red ant here, it can go here. So like that kind of breaks our initial assumption of time is like the distance is greater than 3/2. So you should always choose the ant that's closest to the edge, like backwards closest to the edge. So I don't know if that made that much sense, but anyways, if you keep on choosing the blue ant to go into this corner, what you have is like you're going into like this, right? Let me redraw it. So if you keep on following the blue ant, you do something like this. You're going backwards, and then like you turn, and I'll just assume that every time when you're going backwards, it always turns up or it turns to the left. So like I kind of want to force it into a corner, right? So that means that it just keeps on going into this corner, and and that means that this total area, I mean this total distance, is at most 3/2, right? If the ant was closer to the bottom edge, like let's say the ant started down here, then I would try to force it into the bottom left corner, right? So like it would be something like this, right? And then the total distance would be something like this. So we see that the total distance is at most 3/2. So where does the invariant come in? Well, I guess we used an invariant without thinking about the invariant because we were working backwards. But if you like rephrase this as if we rephrase this proof in terms of going forwards, then we would have an invariant. So we kind of use an invariant without knowing it. So the invariant is if you have like a square and you have an let's say time is t, and let's look at all the ants that are going upwards, facing north. Right, so then where can the ant be? Well, if you like draw some triangles here, and this is side length t, this would be t. You have like these triangles of size t, right? Of side length, these isosceles right triangles of legs t. Then this zone, the ant cannot be in this zone. Because if an ant was in this zone, then by using like the backward process, then you would see that it doesn't work, right? So the ant has to be somewhere in here. So like our ant has to be somewhere in here. And if you notice, and this applies in any direction. So let's just look at, for example, the rightwards direction. If we look at the rightwards ants, if you have an ant like right here, and you have time t, this time let's make time t bigger. Let's say time t is here, so this is t, and then you would have something like this, right? Because t, then you can't have something here. This is illegal, and then the ant would be in that region. And so what you notice is that the first time when these red regions, these bad regions, cover the entire board is at time t equals 3/2, right? At time t equals 3/2, these illegal regions cover the entire board. And then that's just illegal. And then that means that there are no ants on the board at time t equals 3/2, because in every single direction, the entire board is covered by illegal zones. So that is our, I guess not an invariant. It would be our monovariant here. So I guess that's it for today's class. We didn't get to the last example, but that's okay. I think next week's class will be the last class before the summer academy ends. We might have some more classes in the fall, but it would be not in this format because there's school. But anyways, I hope you guys enjoyed coming here, and I will see you guys next week.